So, it's on. Okay, we're going live. All right. Now that we are here, okay. So, back where we left off. We left off at eigenvalues and eigenvectors. Are we totally clear on that part, or are there any doubts, discussions, or queries?
Maybe Turbasu, can you? Maybe you told this, but I missed. I don't know. Where do we need these exactly in quantum computing side of things?
Okay, okay. I'll let Arnav give his thing on that. So, and then I'll add.
Why
Oh,
me?
okay.
Come on, dude. So where we need eigenvalues and eigenvectors and these
Right,
mathematics.
right.
Well, okay, I don't think I'm really the right person to say this.
I mean,
Okay.
how do we apply them?
Okay, so each
Why
gate,
do we need them?
okay,
Mm-hmm.
yeah. So each gate in a quantum circuit is basically a
Mm-hmm.
matrix that apply to the inputs. Okay, let's say there is a qubit, okay, with a value 0. Okay, so it's basically 0 1. Okay, so the input is 0 1. Okay, and whenever it passes through a circuit, it passes through a gate. Okay, what is happening is a matrix is getting multiplied with it. Okay, so every gate is denoted by a matrix, and let's say a poly X gate. Okay, so it's a matrix, as you already know. So whenever you are applying that gate to a qubit, what actually you are doing is, in mathematical terms, you are multiplying it with that matrix. Okay, and the multiplied result is basically the output of that uh, transformation. Okay, so that is
Mm-hmm.
where these mathematical calculations, these different kind of matrices, multiplication, the spin, like are coming into places. Let's say
Okay.
it's in a superposition state. Okay, so the input will not be 1 or 0. It will be, let's say, 1 by root 2 and 1 by root 2. Okay, I think. Okay, so that is what is getting multiplied with the poly X matrices and all. Okay, if
Okay.
I'm right.
Just more clarification on that is that let's say let's say we are applying some sort of a general rotation, not just a poly axis, but just some general r theta rotation, right?
Mm-hmm.
And now we want to see that what is the state of my circuit after these rotations. So what am I essentially doing? Well, essentially, well, I'm trying to apply a rotation to a vector, and that vector is supposed to be belonging to a Hilbert space, right? But what does that mean? Okay, so that means that I want to find what is the final direction of this space, or the final direction of this vector, once I've applied that rotation. And that's essentially where my poly gate, the eigenvectors of my the eigenvalues and the corresponding eigenvectors of my poly gates come in. And what we have is that once we have that eigenvector and so on and so forth, we'll be better off at designing our entire thing. Uh, um, uh, for example, I recently participated in that QHack competition. I'm not really sure whether you're aware of that, but we were one of the variational problems that we were faced with is basically it's called a variational quantum eigensolver. What that does is basically it takes a Hamiltonian, which means it takes the mean or the total energy of some n body system. Here we have a two body system, right? Which is an
Mm-hmm.
electron and a positron. And now what we're going to do is that we're going to minimize that with according to an ansatz. So what is an ansatz? An ansatz is essentially is to find where is to guide what sort of rotations am I gonna do such that my entire system is gonna be decomposed, or such that my entire system is to go from I'm sorry, from some state of some state of my problem to the ground state, and that is the solution of my entire variational quantum problem. And that is in fact where we deal with eigenvalues and eigenvectors the most. What set of operations are you going to give such that you have an eigenstate which is equal to the ground state of our two body system? And I see Shaptoshi has joined, and Shaptoshi is one of my friends, and he's been joining in. He just like asked me today that what are you guys doing, and I told him that we're going to have this session, and he was dabbling in quantum computing. He's from a physics background. So hi Shaptoshi, how are you doing? So am I audible?
Yes, you are.
Okay. So I guess people like Shoptoshi and all are better suited because they know the quantum backstory that goes into all these, right? So I can give you an algorithmic standpoint, but I cannot give you what goes in under the hood. Um, so does that make any sense whatsoever?
So I understand that we use it to find the appropriate gate or
Right,
theta that we are
right.
going to apply
not
to
not the
our
theta, not the theta.
not the
We're
theta.
gonna
Okay.
no, we're gonna generate an eigenstate, which means a generalized state of eigenvectors, which essentially gives me the entire set of the entire ground state, which spans my entire ground state. Does that make sense?
Okay. Yes. Thank you.
Okay. Any other questions? Anything, whether it be why am I doing this, or existential. When we're all open to discussion. I think the Jale's question was actually very nice, and we all should keep in mind why are we doing all this. Okay, so all right. So I think we can like see what's in store for us. Hopefully that will make a little more sense as we go. So we've seen that we already know rather that we have an eigenvalues and corresponding eigenvectors, and how do we do this? I think we know that we take our operator and then we or matrix, and then we subtract it with a lambda times the identity matrix, and then we find the determinant, and then we get a set of values. These are our values with some sort of multiplicity, and once we get those, we'll be able to see that okay. So if our value is so, we'll get a corresponding eigen vector, which is essentially the solution to an equation ax equals 0, right? So what does that mean? That means that we're gonna be getting a set of values which will plug into our matrix, and then we're gonna term that as the eigenvectors. All right. So a very interesting thing about this is that it's used in diagonalization, so in or the diagonal representation for operators. And how do we do this is essentially is that we take a, and that is equal to the summation of all eigenvalues and multiplied by their projections. So we'll come to know that this itself is the projection operator over here, and this is entirely how our eigenvalues are, or rather that how our vectors in our operators are like projecting upon themselves, right? So I have a specific section dedicated towards projection operators, but full disclosure that I am not a physicist, so this makes as much sense to you as it makes sense to me. So I'm just trying to like find the, yeah. So if you guys think that okay, this sounds off, So please let me know, because I am in the process of learning as much as you are. Right. All right. So, but why do we need diagonalization? So, first of all, let's see that where does this come from? Because this was in, I think it was in 2.1 point something, which is
It is in 2.1.6. It should be the projector operator.
no,
And
the eigenvalue representation. Okay, so yeah, 2.1.5. Look at
yeah.
the second paragraph. A diagonal representation for an operator A on a vector space V is a
Mhm.
representation which is given as so. So where does this come from? So we know that this is essentially the projection operator over here. And now what is happening is that once we diagonalize the matrix, that will leave us with nothing but the eigenvalues of the matrix, and correspondingly, once we get that, we'll get our projections and in this form, right? I'll give you why do we need to diagonalize the matrix, but is this scenario clear, that what is happening behind the scenes? Uh,
Yeah,
I mean, you
seems to
guys
be.
can join in. You guys need not like put off your microphones or switch off your microphones or something. It's not a very formal discussion as it is. So you guys feel free to join in. In fact, Tanvir can also join in if he's available, or no. I don't know.
It is clear to me. actually.
Okay, okay. So okay. So why do we need to diagonalize the matrix? So here you can see that these are particularly useful for eigenvalue problems, as the eigenvalue coincides with the diagonal entries of the matrices, and essentially the diagonal entries of the eigenvector correspond to the eigenvalue. So let's look at it a little more deeply. So this is a crash course on diagonalization. So okay, so this got uh, left over from my calculations. So you're faced with the problem. We're faced with this problem where we are supposed to find the sixth power of some operator. So what is the sixth power? You're doing that operation six times, right? And can someone like just go ahead and help me out over here? What is happening over here? Or like at least help me with the calculations. So let me just write it down. 1, 1 minus 2, 4. This is 1, 1 minus 2, 4 again. 1, 1 minus 2, 4 again. 1, 1 minus 2, 4. 1, 1 minus 2, 4. 1, 1 minus 2, 4. All right. So we'll take it in pairs because that makes much more sense. So this is 1 plus minus 2. So this is minus 1. And then this is 1 and 4, which is 5. This is minus 2 and minus 8, this is minus 13. And this is minus 2 and 4, which is 16, which is minus 14. I guess is minus 14, or minus 2 and 16. Also, it's 14. Okay. So we do that 3 more times, and we get something like so. I hope my calculations are right. I'm not very keen on my calculation skills. So what happens is with this is that it gets extremely large, and we have lost all motivation to do this. But what happens when we have something given to us? So let's say that okay, so you now calculate a to the power 6, where a is 1, 1 minus 2 and 4. This time, given that there is a is represented by p times 2003 and p inverse, right? So this can be referred to as the diagonalized quantity of my operator. and what we can make out of from here is that, okay, so given is P is so and P inverse exists and P inverse is so. All right. So how do we do this? Is that we let this be called as D. So let this be called as D. And now since we have a to the power 6, so we have PDP inverse, PDP inverse, and that goes up to 6 times. So essentially, we take that and look at that, how beautifully P inverse and P just cancel each other out, and we are just left with P D to the power 6 P inverse. Now you're going to say that, okay, so how do we compute this? So we come up with a general rule that if my like entries of my matrices are diagonalized, that essentially means, so if this is a00b, and if I raise this to some nth power, that's gonna be like a to the power n00 b to the power n. So that makes much more sense. So okay, so what does this come to? This comes to that this is my p, and this is my p inverse, and this is my entire 2 to the power 6 is, I think it's 64, and this is 729, and accordingly we can compute this much easierly and much more like simpler than we computed this previous time, right? I'm not going to compute it. So if you guys like want to go ahead and solve this, feel free, but you guys got to dictate me every step. Okay, so any volunteers? Okay, maybe not. All right. So we say that a square matrix is said to be diagonalizable if A is uh, similar to some diagonal matrix that is of the form A equals P D P inverse, where P is invertible and D is a diagonal matrix, right?
Can I
So
ask something?
yeah, go ahead,
This PP inverse,
right.
it's gonna give identity matrix, right? So can we write A equals to D, I, and I?
I didn't quite get you.
This P and P inverse, it's gonna give an
uh,
identity matrix. Am I right?
uh, right, but where do you think it's going to be giving an identity matrix? Like, okay, so let me just have it over here. So A equals P D P inverse, right? Now what happens?
I'm not sure. Like, does this give a identity matrix? This PP inverse.
No, that doesn't. It doesn't, because essentially that is A, and A is not an identity. So this is just a representation. So this is just I'm representing it in such a way so that I have something called, I have a matrix P, and which is invertible, and that which means that I have an inverse, and I have in doing so I have been diagonalizing this matrix the entire time. Yeah.
I think if there wasn't a D in the middle, it would give us identity matrix. But
Yes, that is correct. That is
as we
correct.
have D in the middle, we can't have the identity matrix in this
Right. Right.
representation. I understand like that.
Right. Absolutely. So I think Devgandhar got confused in this thing right here.
Yes.
Was it?
Mhm.
Yeah. So
Probably that one.
what is happening, since these two are adjacent? So we are essentially taking two adjacent P inverse and P, and then we are converting that. So okay, so that's I. We are doing it this way. Does that make sense?
Yeah, it's clear now.
It's clear? Okay. All right. So what we're going to do now is that, so we're going to study that when is a matrix A diagonalizable. So in essence, we had our operator, which is 1, 1, minus 2, and 4, and let's just find our corresponding eigenvalues and eigenvectors. So that's easy enough, right? So once we do that, we get our eigenvalues as 2 and 3, and for that we are going to be getting our eigenvectors, which is of the form t 1 1 and t half 1, right? So this t is variable, so this t can be anything since these are all vectors, but they have to be of the form 1 1 or half 1, right? So this is for t equals 2, this is for t equals I mean for lambda equals 2. I'm really sorry. So for lambda equals 2, and this is for lambda equals 3, right? All right. So how do we make sense of this? So let's say that, okay, so this t, let t equals 1. So t equals 1. So here we have 1 1, and now let t equals 2. So we have 2 times half 1, which is equal to 1 2, right? And now look at this, that if we amalgamate these two eigenvalues, we essentially are getting eigenvectors, we're essentially getting our p, right? So that's something which is very nice. Yeah, go ahead.
I couldn't catch it, Turbasu. How did we? Okay, I understand we found the eigenvalues with the determinant, and
All right.
then in the second row, no, just go down below. Okay, yes. So you gave t is equal to 1,
Yeah.
and t is equal to. I couldn't understand that part. How did we
So
come up
okay.
with that?
We came up with that in the sense that this essentially what we're doing here is we are constructing our matrix P, and remember that matrix P has two parts. P must be square, and P inverse must exist, right? Now what's going to happen is that how are we going to do about this, go about this? So we're going to go about this by saying that, okay, so if I take my t equals 1, since we have t over here and t over here, and they can be really anything, right? Because t is essentially complex here since we are dealing with Hilbert spaces, right? So t can be anything. So I'm saying that, okay, out of the blue, I'm going to say that t equals 1, and then t equals 2. So we get two vectors, which is 1 1 and 1 2, right? And we are now, these are our column vectors, and once we have a series of column vectors, we're going to be saying that, okay, so if these are our column vectors, we're going to put them together in a matrix, and this is our p. For the record, t could have been anything. If t equals 2, and for this matrix, let's just say this is t1 and t2. So let's t1 equals 2, then we could have had 2 2, and if t2 equals, let's say, 4, then we could have had 2 1, right? I'm sorry, 2 4. Yeah,
Okay.
right. But for these two representations, we are going to have a different diagonalized form than this.
Okay, different D's. Okay.
Yeah, different D's for this. Does that make sense?
Yes, thank you.
Okay. All right. All right. So let's generalize. So we have our set of column vectors, which is v1, v2, so on and so forth. These are column eigenvectors. So let me just add that in. So this is our column eigenvectors, and in the process, what we are essentially doing is that we're taking that set and we are just amalgamating them. So this is our column vector 1, column vector 2, and so on and so forth to our nth column vector, and we're just putting it in the matrix. Remember, these are all columns, right? So these are of the form this and this, right? And in the process, what we're going to be doing is that, since this is our n by n matrix, a square matrix, we're going to be taking some sort of conjugate transpose of that, and that is essentially what we have done over here, right? And that's our inverse matrix. That's our inverse matrix, and that's essentially our this sort of column vector, which is essentially another n by n matrix, right? And this is our diagonalized values and all. Like this is our D, matrix D, right? So is this part
Mhm.
clear, or yeah, it's very difficult to work without feedback. I'm really sorry for poking all of you. It's really difficult to work without feedback.
No, it's okay.
Okay. So what we are going to be doing now is that, okay, so an n cross n matrix is diagonalizable if A has a linearly independent eigenvector set of eigenvectors, has a linear set of uh, eigenvectors, has a set of linearly independent eigenvectors. Yeah, I think that makes sense. Now note that over here, what we have done over here is that these two, are they linearly independent? If so, then we can say with certainty that our matrix is diagonalizable, right? Now, what does our second theorem say? Is that in fact A equals P dP inverse with D as a diagonal matrix if and only if the columns of P are n linearly independent eigenvectors of A, which we have done over there. In this case, the diagonal entries of D are eigenvalues of A that correspond to respective to the eigenvectors in P, right? So what does this mean? This means that essentially what we are going to be doing is that this over here. So our entire backstory and crash course in diagonalization has led us to this point, right? Does any of this make any sense? Or no, Dev Gandhar?
Yes.
Because I don't want to pressure Jale. So or no, Dev Gandhar, Tanvir, anyone.
Yeah, I get what's happening here.
Okay. What about Dev Gandhar? Do you still have any doubts, any queries regarding this?
No.
Okay. Okay. So we shall proceed. Okay. Okay. So next comes a very interesting topic is our Hermitian operators. So before we compute or know what are Hermitian operators, is we're gonna find the Hermitian conjugate, right? So what are Hermitian operators? So suppose A is any linear operator on a Hilbert space, and there will exist a unique linear operator A, dagger. So this is called a dagger, right? On V such that all vectors VW belongs to V. The inner product this shall hold, right? So this is by definition what do we mean by a Hermitian conjugate, right? Or the adjoint, however you put it, right? And remember that this is for although it's not mentioned here at any point, this is for a bounded linear operator, just not for any linear operator. This is for a bounded linear operator, because if we were to be going from discrete spectra over here to continuous spectra, which translates roughly to, here what we are doing is that we can count our qubits, 0 1 2 3 4 and so on and so forth. If it's a two state qubit, then we call that as a qubit, and if it's a three state, then it's a qtrit, and then it's a qdit, and so on and so forth, right? But what happens in continuous variable quantum computing is that you have a qubit which is represented by I, and I is a rational over and I is a rational, and for that we have weird properties coming in, like connectedness, like what is a connected Hilbert space, what is the completeness axioms look like, what do the operators look like there, and stuff like that. Yeah, so we won't be going over that, and we just focus on discrete spectra for now, and look at what an adjoint is. So an adjoint of A is basically a Hermitian or self-adjoint, or like an operator A whose adjoint is A is basically a Hermitian or self-adjoint. So what this means is that can we just look over here? I don't think I can fit them in the same screen. Hang on one second. Yeah, okay. So for these two, we have that if we have for the inner product V and an A operating on W, then this is equal to the dagger operation of V and W and this inner product. And here we are essentially substituting our value of A dagger with A, because over here A dagger is equal to A, right? So this is how we are going to be defining what is a Hermitian operator. And then yeah, if anyone has anything to say.
Yeah, Turbasu, I just wanted to ask something from the book.
Yeah, go ahead.
After this definition, this V, comma A W definition, it says that from the definition, it is easy to see that AB dagger is equal to B dagger, A dagger. It wasn't easy for me to see that. Is it important to understand that part, do you think?
Yeah.
Because I couldn't understand it.
So do we know what this yields? Does
I thought
anyone know what
that yielded to A dagger, B dagger, but it is not the case.
No, that's not a dagger. That's the transpose.
Ah, no,
that's
okay,
the transpose.
Okay.
Can anyone help me out? What does that mean? So this essentially, in essence, this is supposed to mean this, right? So it follows from how do you define the transpose operation? So if you are going to be doing the transpose, our matrices are flipped, right? So it follows from that property itself that A dagger, B dagger, or A B dagger is equal to B dagger, A dagger, right?
Okay. Okay.
So as we have seen that the adjoint or the dagger operation of a ket is essentially a bra. So with this definition, we can see that if we are going to be applying that to an entire system over here, so if that's our system and we're going to be applying a dagger operation, that's going to yield something of the form so, and that's going to be a dagger operation. I'm sorry, the dagger will be here. Oh, yeah. Now we could. Right.
Okay.
So does that make sense? Does that? Okay. So
yes.
We can see that like a very interesting two of our most interesting properties of our operator or the of the adjoint is that it's antilinear, which means that if you do this sort of thing, then on a linear combination, then it's gonna still retain that, because what's going to happen over here is that if this were to be linear, then this sort of thing is going to happen, but this isn't the case over here. So this is antilinear of the adjoint. So antilinearity property, it's easy to prove enough. It's easy enough to prove. No worries about that. But you got to keep this in mind. And if we do the complex or the Hermitian conjugate twice on the same operator, then we're going to get back the same operator, right? And okay, so a very nice example of this is, as we have seen, as we have mentioned here, is the projection operator. And what are projectors for discrete spectra? So I'll come to that. So essentially, what is happening over here is that let's say our system, or we have just one k, right? So k equals 1. So our projection operator essentially is this, right? Now what we are going to be doing is that we're going to take a vector, right? So we're going to take this vector, or let's just make it look more quantum. So let this be a vector. So this is gonna be so, right? Now note that this is our inner product, which essentially means that this is dij, which is the Dirac delta function, and this is equal to 0 when ij is equal to equal, and when it's not, I mean it's 0 when ij are not equal, and 0 when ij are equal. Otherwise, if it's not orthogonal, it's going to be giving us the projections of A in the direction of whom? In the direction of our I vector, right?
Mhm.
Does that make sense?
Mhm. Yes.
Okay. So how do we go about this? Is that we already know that we can express each vector of the Hilbert space as a linear combination of the basis vectors, which Cn belongs to C, where C is complex, and essentially let this be any quantum state, and we essentially have a linear combination as so. And so we now apply some sort of bra notation, or some bra operator on both sides. So we are taking it over here, which means that we're going to be taking on here as well. So this now note that this phi m and this psi m and psi n are essentially can be uh, orthogonal, or they can be projections of that vector. So what we can see is that Cn itself are those projections, as we have seen when we were deriving the Gram-Schmidt orthogonalization process. That's we are going to be getting some C's, and those C's were the projection operators. And these are essentially the transition amplitudes of the state from psi to the state psi n. And I'm not of the background to like say that why is this so, and why not. We need to have a physicist who can explain this. But yeah, so this is the transition amplitudes, and if we apply this to our first equation, we're going to be getting something of the sort: psi is equal to this psi n and the psi along the vector psi. So along the vector psi n, so we are measuring for the projection of psi to psi n. So this is our essentially our projection operator. Okay. So is this is does any of this make sense?
Maybe can we give an example in terms of
Okay.
states 0 and 1, or because I
Okay.
couldn't understand how do we
Okay.
use these.
Okay. So we have these two states, right? And we need to find our projections of psi to some basis state, right? So let's say that we have our let's say that we want to find our projection on the state 0. So what are we going to do? We're going to be so what we're going to be doing is that we're going to be or I'm not going to say measurement, because that's something similar, because what we take is projective measurements, but yeah. So what we are going to be doing is that okay. So if this we are going to be taking it along the state psi, so we are going to be saying that okay. So if this be the case, right? So
Mhm.
so this is our projection n, right? And
Mhm.
if this be the case, then we have our zero ket and zero, upon which we have our entire psi is alpha 0 plus alpha 1 1. Now note that these two will cancel out because they are orthogonal to each other, and so
Mhm.
we are going to be left with our 0 I mean, I'm really sorry. So we're going to be left with our alphas. And what are these alphas? These are our projections. As we know that these are our projective angles, or should I say that these are our projections on the state of alpha. Because in essence, what we are going to be doing over here in a qubit, what we have is essentially something of the sort this. So cos theta 0 plus e to the power I think e to the power I sine theta, I guess. Not not really not really confident on this part, rather. E to the power I sine theta 1. Right. Is this correct? Can anyone just give me a heads up?
I
Or no,
guess
they've gone the
correct. I guess I'm not sure.
right.
I
So
guess this
so
is
the
I'm not sure either, but
so
yeah,
what we are getting over here and here are, we are essentially taking the projections of these angles, right? So we're essentially taking the projections of these vectors on the state. So in a block sphere, let's say we have a block sphere. So if we have this qubit over here, this is probably going to give us our cos theta, right, in the
Mhm.
state 0 and state 1, right? And this angle over here, if this is theta, then the other will be 90 minus theta, and that will be sine of theta, right? And we'll see, and we'll actually see that why are we going for or either this or this or just this, right? I'm sorry that I'm not brushing up on my basics, but either this or this, right? So
Okay.
what's happening is that we're essentially taking our projections on either this zero ket or one ket over here. So either the CO state, we'll go through this in more detail once we are dealing with measurements. Thank God that that is not my part, and I think Doipan Da has already like volunteered for that. So that should be very interesting. That should be very interesting.
So we
Okay,
use projectors for measurement purposes.
right.
Did I
That's
understand?
basically some there are some 2 to 3 different types of measurements, and this part
Mhm.
what we can see over here is, or what we do on the on any Qiskit or any quantum library is that we take the projective measurements of the angles, or the projective measurements on the qubits. That's essentially what we're doing,
Okay. Okay.
right? um, Full disclosure is that I haven't been able to make notes or go through the rest of the part because I was supposed to go through that today, and well, things got a little messy today, and I'm really sorry, and I apologize profusely for that. But yeah, I will be going over tensor products and uh, a, a very important result, which is our spectral decomposition theorem. And
Mhm.
then in the next day, does that make
Yes,
does
sure.
that Uh, or if Jale has gone through, you can like take over from here. I have no issues.
I've read them, but I'm not able to explain them to the group
No, no
because
problem, no
there are
problem.
words that
Why don't we just
because
discuss them? What have we like studied? And if things get a little out of
yeah.
hand, then we can say that okay, we need to read this, and then we can sit together for this. Does that make
Mhm.
sense?
Yes, as far as I read, we use tensor products to represent the combination of more than one qubit system,
Uh-huh.
as far as I understand. And for, let me check a little bit. But the individual exercises and the formulas that I
Mm-hmm.
couldn't understand in detail. Maybe somebody else, if somebody else knows those in
Okay.
detail, a little more detail than me, I can discuss and I can participate.
Okay.
Mhm.
Why don't we do this? That if you feel it's right, then we'll be putting this off for the next meeting, and then
Yes,
and
that would
then
be great.
and
Mhm.
and then why don't we do this? That why don't you take this session, the next session, and then I'll obviously be there to like back you up, and we all gonna be there. Like even Arnav Devgandha will be there to like back you up on what's going on and what's not. Does should that be comfortable for you, or like I'm just putting
Um,
you somewhere?
Maybe I shouldn't be explaining because they're a little bit advanced for me.
Oh, okay.
So yeah.
So the principle on how this works is that if you are like explaining to someone else, and uh, if that makes not a lot of sense, you'll be getting that confidence that okay, I have read this and I know this, right? So that's kind of motivating. Does
Yeah, yeah,
Orno what's
yes,
or someone can like join Jale on this?
yes, of course. But I really don't understand the half of the things that I read. That's why I'm.
Okay.
Normally, I volunteer to explain things, but in this linear algebra part, I'm not very confident.
Okay. No problem, no problem. Okay, okay. So let's just keep this off, and we'll stop here, and we'll keep this off for the next day. And there's something to like announce is that our I'm still in my fourth year, and Devgandhar is in the I think he's in the second year, and
Yeah.
we got our semester exams announced, and for the seven semesters, and so I wouldn't be getting a lot of time, but I'll still try to make sessions. So
Mhm.
what I'd suggest is that can from now till March, can we do like at least for me, can we do like one session so that it becomes
Sure.
easier for everyone to read the material as well as accommodate ourselves, because I mean, is that was that too selfish? I don't know. Does that
No, no,
did that sound too
no,
selfish?
For
no.
sure.
It doesn't. It's perfectly okay. Trubasha.
Okay,
For
okay.
me, at
So
least.
okay. So we'll meet again on Sunday, and we'll be discussing our backlogs. And before we go any further, we'll be discussing all the questions. Right? Will that be
Okay.
okay?
Yeah, sure.
Yeah. Okay.
Yes, of
Okay.
course.
Yeah. So we'll stop here. And thanks for joining.
Thanks for explaining all these. Thank you so much.
Yeah, yeah.